In this video, we talk about the properties of logarithms. Logarithms are very strange kinds of functions where you're basically undoing an exponential function. Let's look at the two forms and compare them. In an exponential function, we have a base, which is being raised to a power and gives us the answer part. I know that sounds kind of silly to call it the answer part, but that really is what we call it. I'm sure it should have a better name than that, but that's all I've ever seen. This is what is known as exponential form. Now we need to undo this exponential form and write it in what's called logarithm form, or log form for short. In log form, we reverse the relationship between the parts. We write either log or we write ln, and then next to it we put the base, but it's below and to the right. The base on a ln is always e, which does not need to be written. Next to the log, as if it were on a number line or on a sheet of paper with lines on it, we write the answer part. The log of a certain base of an answer part gives us the power. It equals the power. That's what it's equal to. So the natural log, base e, of an answer is going to give us the power. This is the same power that you have in the exponential form in the exponent. Let's now start and look at problem number 1. Rewrite the equation in exponential form. The base is 5. The power is what the log is equal to, which is the x, and it has an answer of a. That's really it. It's just a matter of learning how to convert one to the other. Let's look at number 2. Rewrite the equation in exponential form. The base is x. The answer part is 2. I lost my n. Answer is 2, and the power is y. That means that I can write x to the power of y equals 2. Don't go by based on what's in the position. Go by the position itself. That means that if I put something silly on the test, like log base happy face of star equals heart, you should be able to convert that to happy face of power heart equals star. Let's move on to the next problem. In the next problem, we're to rewrite the equation in exponential form. Again, we look for base raised to the power equals the answer. We go based on position, not based on what's there. That will be a is the base, the power is negative 13 because that's what a logarithm is the power, and it equals b. That's really all there is to it. Let's do the next. Rewrite the equation in exponential form. The base is 15 because it's next to the word log and below it. The power is what the log is equal to, so that's a. And the answer part is 144. That's all there is to it. I wish I could make it harder. No, I really don't. I'm glad that you finally have something easy to do because the last couple sections were not all that easy. Let's take a look now at the next one. Rewrite the equation in exponential form. This has ln. Remember that when you have ln, which is sometimes handwritten with a cursive L, this means that the base is always going to be e. E is a special number like pi, and it's called Euler's number. And Euler is spelled E-U-L-E-R for Leonhard Euler, who was a German mathematician who did a lot of work with these. Our base is not written, but it's understood to be e. The power is what the natural log is equal to. So this becomes e to the a power equals b. In the next problem, we're to write this in logarithmic form. The base is not e, so I do not use ln. The base here is 2. Since the base is 2, I'm going to use log and write the 2 next to it and to the right. The power is a. That means that the log is equal to the power, so on the other side of the equation I put equals a. The answer part in exponential form was b, and that goes next to the log in logarithmic form. In this problem, we're to rewrite the equation in logarithmic form. J to the c equals b. Again, ignore what's there and go by position. This is j raised to a c power equal to an answer of b. Since the base is not e, we use log instead of ln. Log, the base is j, the answer was b, and the power that got me there was c. The log equals the power. Let's look at number 8. Rewrite the equation in logarithmic form. To write it in logarithmic form, I look at the base first to see if I need log or ln. The base is x, so I write log, base of x, equal to the power, which was -3, and the original answer was a, which goes next to the log base x in logarithmic form. Looking at problem number 9, we want to rewrite the equation in logarithmic form. This one is not written terribly well, partly because it's too large, the exponent, for the font. What we need is 11 to the -7/15 power equal to the answer of m. In log form, since the base is 11, we'll write log and not ln. The base goes to the right and below. The answer part goes next to it, which was m, and the log is equal to the power, or the exponent, which is -7/15. In the next problem, we're to rewrite this in logarithmic form. In logarithmic form, we look at the base, which is 13. Since the base is 13, I write log, put the base to the right and below, then I put the answer part next. This time my answer part is a fraction, but that doesn't matter. It's in the answer part position, and it goes in the answer part position in log form. The power over here was n, and so the logarithm is equal to the power. In problem 11, we're asked to rewrite the equation in log form. We have e to the a power equals b. This time, my base is that special number e, sort of like pi. It's not pi. It's about 2.718. So I write ln instead of writing log. Now I don't need to write the base because it's understood to be e. I can only use base e with ln. Now I write the answer part next to it, which was the b, and set that equal to the power, which was a. Let's take a look at the next problem. Solve by converting the logarithmic equation to exponential form. This is an equation because we have a left side, a right side, and an equals. In order to solve it, what we're going to do is we're going to convert into exponential form and then simplify. The base is 5. It's being raised to a power of 3, and it equals x. Since I know that 5 to the third is 125, this tells me that x is equal to 125, and this is my answer. Let's take a look at the next problem. In this problem, we're asked to solve for x by converting the logarithmic equation to exponential form. Again, we're going to convert by taking the base, which is 3, raising it to the -6 power, and setting it equal to x, the answer part position. Now, 3 to the -6 may be one you're not familiar with. If you're not familiar with it, grab your calculator like I'm doing right now and figure out what 3 to the negative 6 is. That's not one I happen to know. 3 to the negative 6 is going to be a fraction because of the negative. This gives me the fraction of x equal to 1 divided by 729, and that's my final answer. I prefer that you leave it as a fraction rather than changing it to a decimal. Let's take a look now at number 14. Solve for x by converting the logarithmic equation to exponential form. On this particular problem, it's a little hard to read, but it looks like it's 18 being raised to the second equal to x. 18 is the base. The power is what the log is equal to, so that's the second, and it equals x. Now I need to know what 18 squared is. Back to the calculator, or you can do 18 times 18. 18 squared gives you 324, and that's your final answer for this problem. Let's take a look now at problem 15. Solve for x by converting the logarithmic equation to exponential form. There's no base written here, nothing below and to the right, but it does have ln, so I know the base is e. E is being raised to the second power, and I set it equal to x. E is an irrational number, which cannot be written down exactly, which means that I'm simply going to leave the answer in exponential form of x equal e squared. Now I want to use the definition of the common and natural logarithms to simplify. A common log is one where the base is 10. A common log looks like log of a number equal to the power. It doesn't have a base written, and the base is understood to be 10. This is for historical reasons, because historically it was easier to do things with a base of 10 than other bases in the days before we had calculators. I know that seems a long time ago to you, but believe it or not, it was in my lifetime, and I can remember having to use tables to look these up. So what we want now is we want to find out what this is equal to. The easiest thing to do is to give ourselves a variable so we have something to put in that position. This means I have 10 being raised to the x power equal to 100 to the third power. Again, take a look at what the form is on the left. There's no base written, but it's not ln, so it's not base e. It says log, so our base must be 10. Then we take the 10 and raise it to the x power, which was our unknown. This is equal to 100 to the third. In order to solve this, I need to write both sides as powers of the same base. I know that 100 can be written as 10 squared, so I replace the 100 with 10 squared, and that gives me 2 powers on the same base. Then I can multiply the powers together to get 10 to the sixth. If 10 to the x equals 10 to the sixth, then this must mean that x is equal to 6. Let's take a look at the next problem. In this problem, it says use the definition of common and natural logarithms to simplify. Log, no base written, 1,000 to the fourth equals some unknown. We'll give ourselves a variable to go for. Now what I need to figure out is, what's the base? It's log with no base written, so the base is 10. Converting into exponential form, I have 10 to the x is equal to 1,000 to the fourth power. 1,000 has 3 zeros, and that means that it can be written as 10 to the third, also raised to the fourth. 10 to the third to the fourth, multiplying the 2 powers together gives me 10 to the 12th. If 10 to the x equals 10 to the 12th, then it must be that x is equal to 12. Let's take a look now at our next problem. Use the definition of common and natural logarithms to simplify. E to the natural log of 1.78. There are two properties in natural logs that are reverses of one another. This says if e and natural log are side by side with nothing in between, not a negative, not a number, not an eyelash, they undo each other, and this will simply give me 1.78. That's it. That's all there is to it. E to a power and natural log base e are inverse operations, and they undo each other. It's kind of like take the milk out of the fridge, then put the milk back in the fridge. Nothing happened. It stayed the same as it was before you did anything. So now we take a look at the next problem. Use the definition of common and natural logarithms to simplify. E to the natural log of 1.35. There's nothing between the e and the natural log, not a negative, not a number, not an eyelash. That means the answer is simply 1.35. This is the same property, but in logarithmic form. Use the definition of common and natural logarithms to simplify. The natural log of e to the 4.29 power plus 5 equals, well, I don't know, so I'll give it an x. Simplifying the left, though, do you see how the natural log and the e are side by side? The only thing between them is the parentheses. The parentheses could actually be dropped so that you have natural log of e to the 4.29 power plus 5 equal x. Notice I left a little extra space so that people would know for sure that the plus 5 is not inside the natural log. Notice that the e is not the base that is written below and to the right, but instead is part of an exponential that's inside of the answer part. That means that the natural log of e to the 4.29 is simply 4.29. Then I need to add 5 onto it so that I end up finally with x equal to 9.29. In the next problem, we're asked to evaluate the base b logarithm expression without using a calculator. On your test, you'll be asked to show your work for this. In order to do it, we'll set it equal to x so we have something to solve for. Then we'll switch forms. I have a base of 2 raised to an x power equal to the fifth root of 2. In order to get them in the same format, I need to get rid of this fifth root. I remember that a fifth root is the same thing as the 1/5 power. Now the format on the left and the right look the same. They're both exponential forms, a base raised to a power. This tells me that x has to be 1/5. Powers are allowed to be any number at all. Bases can be any number greater than 0, but they can't be the number 1. Answers, because of that, are also strictly positive. Evaluate the base b logarithm expression without using a calculator. Same thing. Set it equal to x, take the base, raise it to the power x, and set it equal to the fourth root of 7. Rewrite the fourth root of 7 as a fractional exponent of 7 to the 1/4. That tells me that x must be equal to 1/4. Anything goes for powers, positives, negatives, fractions, anything. Now we want to evaluate the base b logarithm expression, again without using a calculator. In this case, the plus 3 is not a part of the log. So what I'm going to do first is I'm going to evaluate the logarithm base 3 of 1/27 by setting it equal to x. This means that I have 3 raised to the x power equal to the answer of 1 over 27. If I take the 1 over 27 and I write 27 as a power of 3, I can write this as 1 over 3 to the third. But this does not match what's on the left, which is 3 to a number. This is 1 over 3 to a number. To move this to the numerator, I need to change the power and make it 3 to the negative 3. This then tells me that I have 3 to the x equal 3 to the negative 3, which means that x must be negative 3. I can take that part and put it back into the problem for this part, and I get negative 3 plus 3, which must equal 0. The answer to this problem is then 0. Now let's evaluate the common logarithm expression without using a calculator. Again, this has no variable, so I'll provide a variable by setting it equal to x. It has log and no base written. Because it's log and not ln, the base is 10. I'll raise it to the x power and write that it is equal to 0.001. 0.001 can be written as a fraction of 1 over 1,000. You get 1 0 for each of the decimal places. Now that I have it written this way, it is very similar to the last problem. What I do is I rewrite 1,000 as 10 to the third. Each 0 gives me a power. So 3 zeros, power 3. Then I'll take that number and I'll rewrite that as 10 to the negative 3. That means that x must be equal to negative 3. Let's take a look at problem 25. Evaluate the common logarithm expression without using a calculator. In this problem, I have 5 times the log of 100 to the negative 2. I'm first going to evaluate the log of 100 to the negative 2. Now, there are several ways of doing this. In fact, there are lots and lots of ways of doing it. One way is to recognize that the base of this is in fact a 10, and that this is 10 being raised to the second power, the 100, being raised to the negative 2. When the base and the answer part are powers of the same number, you'll get the power. But what is the power? And I'm not talking about the power that the log is equal to. I'm talking about the power on the answer part. Since I have one base there and 2 powers on the answer part, I multiply the powers, and this gives me log base 10 of 10 to the negative 4. This gives me a value of negative 4. You may have noticed that I wrote the base even though I didn't need to. That just emphasizes that the base and the answer part are powers of the same number, 10. This part becomes a negative 4, so I can replace the log of 100 to the negative 2 with the value of negative 4. That gives me 5 times negative 4, which gives me an answer of negative 20 for my final answer. Let's take a look at our next problem. This is the easiest problem you'll get on your next exam, and I promise you it will be there. The natural log of 1. Again, I have nothing to solve for, so I'll put equals x, so I have a variable. The base is not written, but it's ln, so the base is e. Raise it to a power and get the number 1. In a previous video, we kept saying any number to the 0 power except 0 is 1. This is that rule. What power do I raise e to get a 1? The 0 power. This is simply a property that you have to memorize because there's no easy way to derive it. Now we want to evaluate the natural logarithm expression without using a calculator. 25 times natural log of e to the 3/5. Notice that I have a natural log and an e side by side each other. They undo each other and simply give me the power on the e. This will become 25 times 3/5. I can then think of this as 25 divided by 1 times 3 divided by 5. That means I get some cancellation with the 25 and the 5, and my final answer is 15 divided by 1, or 15. Let's take a look at the next problem. Evaluate the expression using a calculator, round to the nearest thousandth. Grab your calculator and enter natural log of 2/7. Be sure that you put parentheses around the 2 divided by 7 so that you don't end up with the natural log of 2 divided by 7. And notice I took a long pause there on purpose because I was emphasizing that we do not want the natural log of 2 divided by 7 because these are not equal. We want the natural log of 2 divided by 7, and that should be approximately negative 1.253 if I round up. And that's the nearest thousandth, which has 3 decimal places. Let's look at our next problem, which is, I believe, our last one. Is there a number x such that the natural log of x equals 10? If so, what is the number? If not, enter D and E. Well, let's think about that. Natural log of x has a graph, which you may not be familiar with yet, but which will be in our next video, which looks like this. It goes up forever. Eventually, it's going to hit 10, which means that there has to be some value out here somewhere that is equal to 10 on that graph. So the answer is yes. How can I find it? What they're really asking you to do is find x. We're going to take the problem natural log of x equal 10 and solve for x. The base is e, it's raised to the 10th power, and that's x. And that's your answer. E to the 10th is the number that when you take the natural log of it, you get 10. It is a very large number. If I plug that number into my calculator, I get something that is very large. It's approximately 22,026.47. As I said, a very large number. Natural log is the slowest growing function of all the functions we have, which you'll see in the next video when we talk about graphs of natural logarithms.